Do you want to hide those two so they're not in your way?
Oh, yeah, I don't know.
There you go.
All
Just
right.
out of the way.
Okay, thank you much. Well, welcome everyone. Dr. Thomas Salver, Dr. Brosius has invited me to present to you on the topics of patents and then codes and standards. And what you'll find is that there's a lot of kind of peripheral information that also arises when we get into discussions of information gathering for technical engineering projects. So I titled the presentation from patents and journals to codes and standards. So patents and journals suggest a lot of the technical information that you will gather up front to begin to scope out your project, see what previous engineers and scientists have done to develop similar type systems. And then as you narrow down on whether you're predominantly electromechanical or some kind of mechanisms, or maybe making use of pressure vessels or thermal interfaces, then you have to begin to identify the regulatory agencies and professional societies that may have codes and standards that relate to your project. And I'll just point out at the beginning, codes are legally binding requirements for engineers or product developers to meet for certain territories of the world, whether the United States abiding by ASIE codes, various national federal regulatory bodies, or whether your product is intended to be sold internationally, then you've got a whole broader set of codes and standards that you may be expected to design to. So I broke the presentation into two major approaches. One is just looking for patents and technical documents or technical journals, and all that stuff, do an overview, purpose, types, format, what they protect, what they might cover, where they may be used, and then we'll end with where to find them. And then taking a similar approach for codes and standards, give a little background information on them, distinguish codes from standards, and they can throw in specifications, but a bonus for that. And then we'll look at regulators by profession, and we'll also take a very high level view of where to find the codes and the standards. But this is very much a kind of a moving target, so to speak. Really depends on your product line, really depends where you expect to sell it or put it to use, what regulatory agencies and professional societies may give guidance in that respect. So I taught this presentation 5-7 years ago or so. We were using the textbook for senior design. I just kind of highlighted this excerpt from the information gathering phase of the project to kind of illustrate what you're really looking at. So on one hand, you've got to start gathering information for your project. Some of you may be resorting to libraries, dictionaries, internet searches, things like that. We're going to focus mainly on the area of resources for this information, such as the federal government or professional societies, societies and associations, as well as intellectual property. So U.S. Patent and Trademark Office also includes copyrights and trade secrets, but these are repositories of technical information that you can use to help guide the design of your projects. So let's kind of dig in. I'll point out, I kind of outlined the ones we'll really be focusing on as technical reports, technical journals, codes and standards, and then patents. And I'll try to get you some tools to help you find those things. So starting with the Constitution, Article 1 says the Congress has the ability to promote the progress of science and useful arts by securing for limited times to authors and inventors the exclusive right to the respective writings and discoveries. So the part that affects you is exclusive rights of inventors to their discoveries. As you're working on technical projects, you're looking for recent and relevant solutions to how it is you might solve the problem that your community partner has presented to you. And you may find some patents that look like a really good solution to your project. But if those patents were filed in the past 20 years, there's a possibility that you'll end up infringing on them. So on one hand, the patent library, the patent office is a really good repository of good ideas for how it is you can solve technical problems. On the other hand, if the inventors of those solutions have filed a patent and provided maintenance fees, then they have exclusive right to produce that product within the US states and territories for as long as they pay the dues up to 20 years of use. So the intent is to share information and promote discovery, but also protect those inventors who spent a lot of the time and energy on perfecting the actual patent that they filed for. So a little background, the Patent Office was founded really at the inception of the United States, first law of 1790. They've made a few revisions really to adapt to changes in technology, improvements, new types, new categories of actual technical invention and all of that. But ultimately what patents comprise are protection or intellectual property rights to a process, an activity method, including industrial technical processes, a composition of matter, chemical compositions, or food ingredient mixtures, or an article of manufacture. And these are very, very broad categories, obviously. You could say that patents are expected to show some level of innovation, whether it's novelty, believe it or not, phones were novel devices at one time. Likewise, airplanes. In this case, you can see novelty, inventive step, or original combination. You know, maybe people had airfoil, motors, or didn't quite pull the airfoil and the motor together until the Wright brothers came up with the idea. And likewise, I think it was the late 90s or so, before we had flat screen monitors and things, there was kind of a famous Apple product. This industrial design was patented in part for the shape and then the transparency, and it's what's regarded as a design patent, which has a little lesser coverage period than a utility patent, which will be, well, many of which we'll be looking at right now. So the type of patent that you're most likely to either need to help work along your project, or that you're reasonably likely to even be able to file over the course of your career, is a utility patent. It's new, useful, non-obvious machine, material, composition, or improvement thereof. And ultimately, by filing with the US Patent and Trademark Office, you're able to gain protection for the design that you developed for 20 years, up to 20 years, if you pay the so-called maintenance fees. Now, referring to that Apple computer stand that I showed on the preceding slide, that's what's referred to as a design patent. And it really protects the way the article looks. So if, say, Microsoft, computer manufacturers say, hey, we want to do something just like Apple, let's do the transparent computer monitor and all of that, sell it in the market. Apple would then respond with the patent infringement claim, suit, I guess, and that outlined the claims that they have listed in their industrial design thing. That only provides 14 years of protection with maintenance fees, and I doubt anyone's astute to Apple configuration, which I'm sure is long since past its period of protection. A third type of patent is a plant patent. And this is intended to protect plant breeders or even genetically modifications to those plants. And it also provides 20 years of protection with maintenance fees. There was, for a brief period, a fourth type of patent referred to as a human gene patent. And it's thought of the 20 to 25,000 human genes, of over 4,000 had been patented at the time of just before 2010 or so. But this was creating a lot of inhibitions to medical process, genetic diagnostics, genetic testing, all those things, that it actually went to the Supreme Court and was struck down 9-0 in 2013. So that fourth type of patent that briefly existed no longer exists, because it was seriously compromising the health and well-being of a lot of people around the world. People were, certain companies with a gene patent were saying, hey, you can't use that, that's ours, we invented that. And arguably, that was already in place long before the patent office even existed. Patents themselves are basically lists of ideas, and it happened that about 5-6 years ago, I was advising a senior design project, and we ended up getting a patent in the process. So this is a list of the patent that we received. It was through UW-Platteville, filed by the UW or Weiss's technical system, and these were for mechanical engineering majors who were closely involved in that senior design project. It was for a microparticle generator developed for US Geological Survey. And so I just took the excerpt of this because it illustrates the main contents in the body of a patent. So on the one hand, we've got the title of the invention, we've got so-called cross-reference, or what's referred to in the vernacular as prior art, statement of federal sponsorship, background, summary of the invention, drawing with brief descriptions, detailed description of the invention and actual embodiment, and then so-called new claims. You can see I put these red boxes around the prior art and the new claims. These are the body of legal statements that give your patent protection if you were to pursue infringement case against someone else, or if you were to infringe upon the patent, these would be the claims through which you'd be prosecuted and perhaps given a hefty fine. So the claims are really the technical, I guess, verbiage, so to speak. It's very much in legal terms, often written by engineers with legal degrees, though. These are the claims on which claims are, cases of infringement and all of that are based. So patents have to provide a lot of information. They have to be written, description of the invention and the way of making and using it. They have to completely explain the mode or principle of operation, enable anyone skilled in the art, that is to say, anyone with the right manufacturing skills to be able to produce it and use it. And they have to provide a complete and specific embodiment of one instance, so to speak, of that patent. Now, this gives rise to some questions in the minds of would-be inventors. Should I file for a patent? Is there enough incentive? Would I be able to protect it fully? Or should I keep it a trade secret? And it really depends on the circumstances of the product or composition of material or whatever that you're looking at. But in part because by filing a patent, you're basically raising it to the public consciousness. You're making it available for everyone to look at and review. And if you've got competitors, let's say you file a utility patent with 20 years protection. If you've got competitors in your industry and you've filed a patent, then for 20 years, your patent is going to be publicly available to them. And they may be like, oh, our competitor had a great idea. Let's start reverse engineering it right now. If we develop the same product and it has the same marketability, then we'll just begin to negotiate a license agreement for you, the inventor, or more commonly your employer, the owner of the patent, to actually license the product and then sell it, mass produce it, and all of that. So, as I said, on the one hand, patent information, patent repository is a really good source of ideas for solutions to technical problems. And sometimes those inventors come up with the best solution for the problem. And you've just got to bite the bullet and say, let's go to their attorney and arrange a licensing fee so we can produce this as well and kind of keep our company in competition with the others. But it really has to include what are referred to as the claims, pointing out and distinctly claiming the subject matter that relates to the invention. And the claims themselves are what define the scope of protection afforded by the patent. So I've worked with a few patent attorneys in the past, and they describe the activity as really looking at the literature, the so-called prior art, and trying to carve out the area in this body of words or information, so to speak, that you, the inventor, can claim as the new portion of your invention that you can then claim as having protection, at least within the United States and surrounding territories. So it does take technical insight and skill, typically, to develop an invention, and it even requires some technical insight to become a patent attorney or a patent agent. So anyone recognize this Swiss patent clerk? Einstein, right around the time he was writing his theories of relativity, he must have had a little spare time at the patent office to think about more abstract things. But college degree in engineering, you're all kind of approaching that deliverable. Good moral character, I hope. I'd like to believe everyone's got good moral character and repute, legal, scientific, and technical qualifications. It is a career option for engineers. It does take a little addition of a legal training as well, though. So Patents are property rights given to the inventor for a limited time in exchange for public disclosure of the invention. So you do end up giving up the secrecy, the trade secrets or things like that, that may or may not be worthwhile to your company. So if you have inventive steps, and it's very common in industry, I wouldn't be surprised if 20, 30, 50% of you end up at least named on a patent. I would be surprised if any of you become multimillionaires as a result of it, because they very rarely give the super financial windfall that we'd all like to have at some point in our life. But they have to serve a useful purpose or form of operation. They have to have a complete description. And this is what prevents a lot of companies from even wanting at some of their inventive steps, because if they can keep it an internal trade secret and not outline the details of the manufacturing process, maybe for something like, I think Gorilla Glass used on cell phone screens is still a trade secret. I think certain competitors have been trying to pick it up, the actual details of the process, but the originators of it have said, oh, let's not put that in the public domain. Let's not get this limited time in exchange for public disclosure. So in cases of patent protected inventions, though, if your company really needs to make use of it, or if you find a solution to a technical challenge over the course of your engineering senior design class, and it seems to be the best solution to the problem at hand, then your community partner will have to weigh the decision of contacting the existing license holder, patent holder, and licensing the product so that they can produce it for sale, at least in the United States and territories. And so you can get exclusive or non-exclusive rights in those cases. But kind of the drawback with patents is way back in the 1800s, that was great because America was kind of a manufacturing hub, at least on this side of the hemisphere. And there wasn't a lot of international trade, perhaps, that could occur, over very brief periods and stuff. So patent protection was a really good security to have at that time, but it only has legal teeth, so to speak, in the United States and its territories. They have no effect, no power in foreign countries. For foreign countries, you'd have to apply for a patent at each country or regional patent office, each of which would have its own patent law. Some of which are more restrictive than the United States as well, in terms of time to file, public disclosure, and things like that. So to give you a little perspective on kind of the state of the world in terms of patent and IP protection, here we've got the unitary patent package that you can see the European Union is gradually consolidating into a members type protection thing. And so in this case, presumably, let's say we've got an invention patented in the United States, only protected in the United States. So Spain could manufacture it and sell it in Germany, or Poland could manufacture it and sell it in France, unless that American inventor had also come up with a European unitary patent package as well, then it would be protected from manufacture and sale in the European Union, at least without the license of that supplier. But as you know, there's plenty of other countries as well, depending on the complexity of the project and the regions where it might be valuable for sales. You may have to file for patents, in this case, the SEAN member countries as well. So you can see as the world becomes more internationally, globally connected and stuff, the protections that patents afford become more challenging. And at least maybe for a company with an international product line, maybe their pockets are deep enough to file at every major patent office around the world. But for independent inventors who may not see a massive return on investment, they may begin to question whether or not to keep it a trade secret, to even bother with filing fees. Is that innovative? What are the cost benefits of filing for a patent? So I can say, having gone through the process, we usually hire attorneys, patent attorneys. They're people with technical background, but also legal skill sets, and they don't come for free. They may charge $500 an hour or so to look at the prior art, look at these, carve out the new set of claims, and then work with the patent agent to actually file those. And then you kind of spend 2 or 3 years sitting to determine whether or not the patent agent even eventually approves your patent. But it really raises a lot of questions, from potential competitors to your ability to even enforce against any patent infringement. And in some cases, having a patent is a bit of a prestigious thing. Say, I'm now registered with the U.S. Patent and Trademark Office. But again, it goes back to, the public disclosure, the 20 years of protection, and then the question is for types of invention, just keep it a trade secret. Should it never leave the factory floor? Should we limit it to these 3 people so we have a little redundancy and nothing else? So the reality is that less than 10% of patents recoup the actual patent costs. And there's certainly the upfront cost of performing the patent process, upwards of $100,000, maybe even more, to make the patented product. You would see a benefit if you were to license, sell the product or sell the patent, license the patent or whatever, and then license the technology. So I've got 4 patents. None of them turned $1 for me. I didn't really expect them to either. But there are situations, at least, where you end up with big companies going head to head with each other in terms of patent protection and all that. So one I'm familiar with was ExxonMobil versus Shell for synthetic engine oils. Massive market. You go get your oil change, you're probably given the option of using synthetic engine oils. Another was Wharf versus Apple. So Wharf was actually the Wisconsin Alumni Research Foundation. It's based in Madison. It was one of the biggest patent infringement settlements ever. I'm going to buzz by it today, but you can easily look it up. There's Schmeisser versus Monsanto. And then one that might seem relevant to all of you is this bionic wrench versus Craftsman. So when I was in graduate school, there was a machinist and design instructor, this Dan Brown, who had developed this multi-size wrench for sockets, bolts, all of those things. And he developed it on his own time. He patented, he started up a US company with a shoestring budget, this loggerhead tools. And eventually he thought, hey, maybe I can market this more globally. So he contacted Sears, who owns the brand Craftsman, which is called America's most trusted brand tool. And Craftsman promptly solicited to a Chinese manufacturer to produce a knockoff that looks very strikingly similar to it. So not only did they not license the invention from this independent inventor working in his free time and all that, they stole the idea and they had it manufactured outside the United States where this gentleman's patent protections didn't apply, and essentially marketed it around the world. So it went to court, a lot of back and forth. It was kind of a ongoing case in that area. And the guy won $6 million against Sears, representing the lost sales in the United States and its territories. Now, Sears continued to manufacture the product and sell it outside the United States without any repercussions. And you might ask, $6 million is big money for the independent inventor, but kind of pocket change for Sears and Craftsman and all that. So this is another case, there's often a lot of discussion and debate on when and where to patent, whether to patent at all. Could the guy have spent an additional $100,000 to get European coverage, another $100,000 to get Asian coverage, and thereby, received a much higher settlement for international sales as well as national sales? But that wasn't the case. But it does kind of convey the story, is if you're looking for something multi-size bolt tightener or something like that, and you're like, hey, that guy's got a great idea, let's put this in our project. Make sure before you go too far, you get the approval of your community partner, or in your future, your engineering managers and all that, because you might just be building your company up to a massive liability that could actually bankrupt the country. So source of good ideas, source of liability as well. Be kind of cautious on how you work with that. Now, continuing on with technical design information, we've got so-called scientific or technical journals. And this is just a depiction of some of the big impact factor ones. So applied physics letters, structural biology, advanced materials. I know the editor for that one. In fact, I've got guidance or technical writing guidelines based on that. Even the American Society of Mechanical Engineers has a multitude of different journals. In fact, you'll find virtually all of your professors have published in at least 2 to 3 scientific journals to get their PhDs, and many have, multitude of 20, 30, 50, 100 or so. They're really difficult. Do you think your final report for this class is difficult? Multiply that times 20 and you'll know kind of how difficult it is to get through the peer review process. But that's ultimately kind of the threshold or that a lot of professors and others have to pass in order to get their credentials. But this is just kind of a survey of the multitude of scientific journals published by the American Society of Mechanical Engineers. So it's really easy to look up. You can type in ASME journals. You'll find this big repository of information, Journal of Fluids Engineering, Mechanical Design, Mechanical Devices, so on and so forth. The benefit of journals is that I shouldn't say all the information in them is free to use, because very often the researchers will publish something in the journal after they had filed for patent protection. That was kind of my situation about 15 years ago or so. Is I had 2 journal articles ready to be submitted and ready to be presented, but we had to get our ducks in a row, so to speak, in patent coverage before the so-called public disclosure, because as soon as it's made public, it's regarded as everyone's to work with. But these also serve as really good resources for information on product design or design of systems. In this case, it was a system that some senior design students and I had developed for U.S. Geological Survey to infuse water with carbon dioxide to prevent the spread of aquatic invasive species. So for patents and scientific, say, publications or journal articles, there's a few resources you can go to. There's U.S. Patent and Trademark Office with their website, which is a little bit bulky and inconvenient to work with. Likewise, there's Compendex. There's a range of different online, journal access resources as well. What I typically go to is Google Scholar, and I've got a little bit of a covering on the top there. So let me see if I can clear this out a little bit, and I'll show you just kind of a quick approach to how it is you can find resources for your products. So let's go in. You saw the hyperlink I provided for Google Scholar. It looks a whole lot like Google, but Scholar instead. I'm going to go to a product line that I'm familiar with, microparticle generation system. And you can see right here, it doesn't provide results from like an ordinary Google search. It has its own algorithms behind this. It selects information more or less exclusively from the technical and trade literature. And so in this case, you can see, core shell microparticles. In some cases, lists by the number of citations. This is often a useful indicator of the quality of the actual technical report as well. But the other thing you have in here is the option to include patents. So here we have kind of the same type of information. What I can type in, a lot of it's seemingly irrelevant. If it's cardiovascular disease, maybe it does or doesn't pertain to your project. We might narrow the keywords and find, even more focused articles. And then I'll just put in, I guess, one that I'm familiar with. On the one hand, we've got, just type in Zolper. Should bring it up right away. So this is the patent I mentioned. Some senior design students and I had picked up at UW-Platteville 5-7 years ago or so. The benefit of Google Scholar is that it gives you patents, and it doesn't give you all the kind of intermediate things of the U.S. Patent Trademark Office. It allows you to download the PDF right away. And you can kind of begin to examine it right away as well, determine whether it's got inventive ideas Or if you think you're coming up with an inventive idea, I forget the phrase, ignorance of the law is no excuse for breaking the law or something. So there's a chance you may independently reinvent the wheel over the course of your senior design project. And if you think you've got a new inventive step, it presents two questions. One of which, should I patent it? The other of which is, has it already been patented? And might I be telling the company to begin to infringe on an existing patent that could then put them at risk of infringement case? So anyways, this is kind of the outline of it. As you can see, there's a very standard format. And somewhere in here, it lists, I mean, this is a specific embodiment of the invention. And then it goes in and it lists, background, as we saw with standard content, summary of the invention, brief description of the drawings shown above, and a detailed description of the preferred embodiment. Listing all of this was done by the patent attorney who had engineering background. And then the very last section of it right here, what we claim is a microparticle generator, blah, 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 so on and so forth, all the way through, and it lists these 20 claims right here. And so now those four students, myself, and the branch chief of US Geological Survey have patent protection on this product from 2019 through 2039. So if anyone needs a microparticle generator or reinvents the process, they've got to license it through the current holder, which is US Geological Survey. So this is what you have to do in terms of due diligence for any substantial improvements to a manufacturing process or things like that. I can point out as well, I'll just type in microparticle generation. When it comes to getting the scientific articles, more towards peer-reviewed technical journals as well, it can be a little bit tricky because journal articles cost anywhere from $25 to $85. I doubt that many of you want to spend that, on something that may or may not be suitable for your project. We certainly have interlibrary loan where you can access virtually every journal article that's listed on Google Scholar. But there's a little trick that you can do if you kind of want to save yourself some time and energy. You can see on the rightmost of all of these, we've got all 9 versions, all 6 versions, all 14 versions. There's actually several different places where these are being published. And if you click on those multiple versions right there, you may be able to fish around and find a PDF. So the authors themselves have the ability to publish their own work on their own website. So you may be able to get the author's draft or version of their manuscript instead of the official, Elsevier or Wiley presentation of the document, which you usually have to pay $50 or so for. So that's at least a recourse or an alternative for obtaining the journal or technical journal information that you might be looking for your project. Any questions on patents and technical publications? Okay, so let's jump to part 2. We've got codes and standards, and I'll give you a little background perspective on those. I don't mean to rush too much, but 20 minutes, I'll try not to run over. Oh, my titles are now covered up. So most of you are probably aware, engineering's really gained prominence and true activity in the past 2-3 centuries or so. At one time, many engineers, did their best. They wanted to design and build products that were safe for the public, but they didn't have really consistent standards and guidelines to work by. So at one time, United States has really been the lead in a lot of engineering fields, really starting in the 1800s or so as a result of our, commercial capital mindset. But here we see an obvious failure, what I refer to the Wild West of engineering. And then another pretty problematic failure in the 1800s. There were a lot of steam engines that were being developed, and even steam boilers placed in manufacturing plants and all that, and they were blowing up. And I think there were over several thousand explosions of boilers in the early to mid 1800s or so, before this group of mechanical engineers formed a society and said, hey, we got to get boiler codes and specs. I know some people who died in a boiler explosion, and it was just happening way too often. And so the American Society of Mechanical Engineers was founded really initially to establish boiler design codes to prevent the catastrophic loss of life and limb that was occurring around the country. Shortly thereafter, I don't know the exact dates and all that, but the American Society of Civil Engineers was formed. As you know, in the early 20th century, electrical topics, engineering and all that really became a field in its own right. So IEEE, and then we've got chemical engineering, ASHRAE, Society of Heating Refrigerations, SPIE, ASCE. These are all professional societies, just voluntary organizations that work together to design standards, so to speak, for whatever technological appliances they have specialty in. And then on the other hand, we've got so-called regulatory agencies. These are usually formed at the federal level, that is to say at the United States government level or international government level, such as Food and Drug Administration, Consumer Product Safety Commission, Department of Transportation, and all that. So these professional societies and regulatory agencies work kind of hand in hand to ensure the safety of the public by very often moving standards into codes. And codes are essentially standards with teeth, so to speak. Teeth meaning they've got legal penalties tied to them. They've been mandated by some governmental organizations as the law of the land. The standard that must be met becomes a code. So here we've got kind of the mix of both professional societies and regulatory agencies that may have codes and standards that pertain to your project. So National Institute of Standards, American National Standards Institute, ASME, American Society of Testing and Materials. All of these may have some lists of standards, maybe for certain alloys of steel, maybe for certain boiler specifications, many of which may become codes, so to speak, for some federal regulatory agencies as well. So National Electric Commission, American Petroleum Institute, I think these are still professional societies. European norm is probably federal regulatory, the whole European Union. Consumer Product Safety Commission, I think that's a federal one, but it makes use of the standards that have been developed by professional societies. And then even these NASA, American Defense Logistics Agency, they'll pull standards from ASME or ANSI or ASTM or Underwriters Laboratory and make them essentially the law of the land as well. So the difference between codes and standards are, you could say a lot of it starts with standards, but codes are the laws and rules, that is to say mandatory if they're legally binding, that help the government protect the public and prevent property damage, whereas standards are generally agreed upon set of guidelines for dimensions, procedures, material composition, and all of that, that are usually articulated by some professional society. So the way it usually works is you've got professional societies building out standards, like ASME built out the boiler standards in the 1500s. They've got huge books on those standards. And at some point, say the Nuclear Regulatory Commission says, you know, if you want to build a nuclear power plant in the US, you've got to abide by these ASME standards for boilers and pressure vessels. Let's make this standard law. And then that standard is essentially a code. There's actually a subdivision of standards as well, referred to as specifications. And these are very often done on a much narrower basis. They're not codes by any means. It's kind of like taking standards and then say if you're contracting with some part supplier or something like that, you may say, build it to this ASTM standard, and then include these specifications, very often like heat treating processes or dimensional requirements or something like that. But in terms of codes, if we were to at least consider ASME codes like boiler and pressure vessel codes, or in this case, gas turbine codes, there's two main varieties. One is referred to as performance test codes, PTC, I think, and then the other is prescriptive codes. Essentially what they are, in this case, it refers to testing specifically this gas turbine engines and using specific procedures to determine corrective power output and exhaust flow and all of that. It's a very prescriptive procedure to make sure that everyone can compare their gas turbines in an apples and apples basis. Rather than one supplier may want to announce certain characteristics of their turbines or skew the information to suggest that they have higher efficiencies and all that. Then the others are so-called prescriptive codes, and this is basically saying, if you're going to build this bridge, you better have this. You better, have this factor of safety of 4. You better have all these justifications and explanations in place. And so codes are legally binding standards. Very often, as I said, a standard can graduate into a code if some federal regulatory agency sees it necessary to give that level of power, so to speak, to that standard. So it becomes a code. But standards in general are, as you can see, rules, testing methods, definitions, practices, developed by experts within each technical field. Very often they help reduce the price of a product. They essentially create these so-called economies of scale where, if everyone who manufactured nuts and bolts decided on their own thread type and pitch and all that, we just have a nightmare at hardware stores. And, you may say, oh, my quarter 20 span, bolt is to this parameter. And others say my quarter 20 is to a different one, but the standards ensure that whoever produces a quarter 20 not a quarter 20 bolt is going to get them to fit interchangeably. Likewise, all of you have used USB devices. You know that there's multiple producers of these around the world, but they're all designing the same USB port standard for inlet and outlet of the USB connection. So that's another very common standard that abides by economies of scales and simplifies supply chains. I had a project in probably 2008 or so. I was working at a diesel supply company, and we were manufacturing these fuel pumps for some company in Germany. I think it might have been Mercedes-Benz or DAF or something, but they specifically said we need an 11-tooth spline on the drive shaft of this hydraulic or fuel pump right there. And I think they gave me something like the DIN standard. So DIN in this case is Deutsch something. It's a specifically German standard that we had to design to. And so on the one hand, I had to send this, make a drawing of this 11-tooth spline shaft there. We actually outsourced it to another company that specialized in shafts. When we got them back, I had to add a specification to it to send it through the appropriate heat treatment operation. So heat it to so many degrees Fahrenheit in the absence of oxygen, and then quench it in oil, and a few other post-processing steps as well. So it was not only a standard, but it was also a specification. Now, getting into codes and the range of applicability is kind of one of the more nebulous topics that we may encounter. I think you've all heard of building codes, and hopefully most of your homes and certainly this university is built to the local building codes. But those, as you would imagine, vary substantially across the country depending on the environment where the buildings are actually situated. So we know the West Coast is kind of an earthquake-prone region. A lot of their particularly tall buildings have very stringent earthquake building codes. Meanwhile, on the East Coast, we know the Gulf and Atlantic coast is susceptible to hurricanes periodically. And so they've got a whole different focus on building codes that are required for inspector and approval in that area. Likewise, any civils in the room? I don't really know the mix of this, but civil engineering obviously have to some highways, bridges, superstructures, steel construction, and steel buildings in the United States. Has to be certified or at least built to the American Concrete Institute codes, American Institute for Steel Construction, and very often American Society of Testing Materials to make sure they've dotted their i's, crossed their t's, and put their ducks in a row. Likewise, electrical engineering is subject to the codes and standards of the National Electric Commission, IEEE, I think it's International Electric Code. If at least their products are being built, manufactured, or sold internationally. And then Underwriters Laboratory as well. Some of you, if you look on a lot of your electronic products, especially household items, you'll see little UL certifications on those. And periodically we do electromechanical projects in this class, and we have to ensure they're UL certified, depending on where they're used and what their power draw is. Likewise, environmental engineering, international standards organizations, Occupational Safety and Health Administration, National Fire Code. In some cases, LEED it's got some building standards associated with it as well. So it's hard to know which codes and standards you have to design and build to. Usually employers, I know most of you probably won't start off self-employed or as engineering consulting stuff. So most of your employers already know the codes and standards for their industry. But in the case of your senior design projects, as we saw, you may make use of patent resources to come up with ideas, or you may generate your own ideas and unintentionally infringe on someone else's patent. So there's a lot of this kind of ambiguity that occurs in engineering in general. Now, ASME is the one I'm most familiar with. They've got their boiler and pressure vessel codes. So the interior of a boiler that might be 6 to 8 feet diameter of steel operating at 4,000 PSI or so. Likewise, heating, ventilation, air conditioning systems. ASHRAE's got a bunch of standards, some of which may be graduated to codes, depending maybe at a state level, maybe at a national level, maybe at a local level as well. American Petroleum Institute, all of those can influence the products that you'd be working on. So this is just one of a multitude of ways of identifying the codes and standards that may pertain to certain projects and product lines. So the website is just asme.org. Not only do they provide scientific journals, but they also provide a repository of codes and standards. You can click on this. I think I went to pressure piping, pipelines, and plumbing, and it brought up a whole bunch of codes. So this is boiler pressure vessel, BPVC right here. All sorts of ferrous versus non-ferrous materials used in pressurized devices, welding rods, material properties, construction of nuclear facilities, and all of that. All around $1,000. So if you, and a really thick book, which you can see most of which are print rather than PDF, because they don't really want those to proliferate too readily out in the public domain. This is an excerpt from Wisconsin boiler codes. I just kind of point out what they have as the standards, for any boilers in the state. They say we refer to not only boilers, but a whole bunch of other things. So B16, ETC, some ANSI and ANST or ASNT standards as well. Perhaps the standard you're most likely to encounter early on your career is the ASME Y1415. Geometric dimensioning and tolerance standards. Have you all seen some of these big symbols for circularity, perpendicularity, flatness, smoothness, true position, and all that? So you're already becoming apprised of the language of standards, at least within American Society of Mechanical Engineers. And as you would imagine, for a very large, say, chemical processing industry or something like that, you have all sorts of regulatory agencies saying, don't let an accident happen. Because when these toxic chemicals release plumes, the people in the surrounding neighborhood could put at risk of certain chemical-induced injuries or life-affecting illnesses as a result of those. So I don't remember this situation. I think it was down in the Gulf Coast. I think it might have been a petroleum processing facility or some kind of chemical processing facility here. Obviously, something went wrong. What code or standard do you think was disregarded? Or let me broaden the question even more, what type of engineers do you think were involved in the design of this system? Mechanical, chemical, or civil would be involved anywhere, and making sure they're not building on sand. Ensure that the footings of these buildings are really secure in the event of a hurricane. So probably electrical involved in there somewhere as well. Environmental, I would imagine they have their input as well. And so that's just the types of engineers, chemical, mechanical, electrical, industrial, civil. Someone had to get contracted, even if this doesn't employ civil engineers, they were certainly consulted. And they had to stamp off on the project every time a new footing was built for those buildings and stuff. So I don't know exactly what the source of this accident is, but who do you think failed to meet the code? Electrical engineer? Civil, mechanical? Do you think some government agency, regulatory agency or something is gonna send inspectors in and track down the root cause of that failure? And do you think you'd want to be the person who didn't do their due diligence or signed off on the project without a thorough scrutiny? So the question then becomes a little bit of humor at the end is who failed to meet the codes? Is it going to be you? Be you? You? No, we know that that's a career compromising event, is to just sign off willy-nilly on the approvals or inspections or code compliance and things like that. It may not send you to jail, but it very well send you to jail too. There is criminal negligence in ignoring engineering duties. And so you certainly don't want to be the person who spent 4 or 5 years studying intensely, working so hard to get a job, and then ends up in jail for 10 years or so. Okay, any questions on it? Admittedly, this kind of a tangled field of regulators and professional societies and codes and standards. But be cognizant of the path you take and feel free to ask your engineering advisors. They may not have the exact answer, but they should be able to point you to the right direction for it.
It was the, no smoking.
And bring them out every day. What? Thank you, Tom.